55. Oh, I think I chose 55 yesterday, so let's do 56. So limit as x approaches 0 from the right, from tangent to x raised to x. Again, I know my target. My target is to somehow get to this situation, if possible. Okay. Any suggestions? So I know this is a different topic, but I just want to trigger your memory. We had kind of similar functions before. A function raised to another function. What did we do with those? Yes, it was a different story. We were differentiating, but the same idea works here. So what did we do? Sorry.
My apologies. We use the natural log.
Absolutely, it's the same idea. Thank you very much. So first step, we have to denote the function by tangent to x to raised to the x by y. Yes, this is step 1. In step 2, we have to apply natural log. In step 3, we are going to apply limit. This limit to both sides. Oh, sorry, I jumped. I'm sorry. So when 0 from the right, tangent 0, this is 0, and the power is 0. So this situation we are looking at is 0 raised to 0. This one. So the next step, I have to denote the function by y, I have to apply natural log, and now I apply limit to both sides. Limit of this, of natural log y, although you will say, wait a minute, this is not what you're asked to determine. You're not asked to determine the limit of natural log. I know. Just keep, watching, and you'll see in a moment what's going to happen. So I apply limit to the other side. So this is x times natural log of tangent to x. I have to test again. This approaches 0. When this approaches 0 from the right, then natural log approaches infinity. Or negative infinity, it's not important. Still 0 times infinity. So I changed, which is a great step forward. I managed to change this into this. And I know that this one only requires an algebraic manipulation to get into one of these two. So then, here's what I'm going to do next. Limit as x approaches 0 from the right. Don't touch natural log. You don't want to put a negative power on a natural log. Exactly what we did before. These two functions are identical, because when I divide by a fraction, I have to flip the fraction. But now, this, as we know, tangent 0 is 0, natural log 0 approaches infinity, so this is infinity. And 1 over 0 is 0 from the right, this is also infinity. So from here, it was a minor step to this. Now, only now I can apply L'Hopital's rule. So this is limit as x approaches 0 from the right. I differentiate the top. I like the denominator. I know what that is. I differentiate the top. 1 over tangent to x times tangent prime, which is secant squared to x, times the inner function prime, which is 2. Okay. Next step. I may have to go to the next page. I will have to go to the next page. Okay, so secant squared tangent 2 can go outside. I have to flip this. Let's see if I can simplify this a little bit. Secant is really not a problem when x approaches 0 from the right. This will approach 1. because it's 1 over cosine, or cosine squared, but doesn't matter. So 1 over cosine of 2x when x approaches 0, this will be 1, secant will be 1. That's nice. X squared will go to the numerator, and out of tangent, after I present it as sine squared over cosine squared and flip. So, for now, I'm going to write limit as x approaches 0 from the right, from negative 2 x squared. I'm going to even drop that, divided by or multiplied. So this is 1 over tangent, which is sine over cosine, or cosine 2x over sine 2x. I continue. Cosine 2x approaches 1. It's not a problem. So then I put a negative 2 outside. Limit as x approaches 0 from the right, from x squared over sine 2x. At this point, I'm just checking my work one more time. So it's cosine over sine over sine, cosine, that's correct. I flip that, 2 is right here. Okay. So now again I have 0 over 0. I will continue. Limit as x approaches 0 from the right. The numerator prime is 2x. The denominator prime is cosine 2x, but times 2. Sine prime is cosine, but the inner function prime is 2. Okay, these two go away. This will approach 1, but this will approach 0. Negative 2 times 0 over 1 is 0. You would have never guessed that, because you probably would have said, oh, 0 to 0 is 1. No, it's not. Not when the base is 0. So the answer is 0, but we are not finished. So I copy the beginning and I copy the end. So this is our step 4. I copy my starting point, limit as x approaches 0 from the right, from natural log y equals 0. I copy the beginning and the end. At this point, I will go back to continuity, chapter 2. Very important. We talked about this theorem a little bit, and we used it in the limit laws. And we called it at that time swapping of the operators. And we've done that several times, differentiating these functions, function to a function. Under conditions of continuity, theorem 8 on page 124, we are allowed to swap the operators. And that's what I'm going to do. I am going to swap the operators. Which operators? This goes in front and this goes in they are swapping places. So then, natural log of the limit of y. Now I am not going to put y, I'm just going to put the function. Limit of this. So limit as x approaches 0 from the right, from tangent to x raised to x is 0. Remember, the natural log has a base. It's a phantom e. E raised to 0 is this. So let me refresh your memory on the conversion between log equations. They are equivalent to exponential equations. Log base a of x is y, which is a log equation, is equivalent, because it goes back and forth, a raised to y equals x. A raised to y equals x. E raised to 0 is this number. So limit as x approaches 0 from the right, from tangent to x raised to x is e raised to 0. And how much is e raised to 0?
1.
Very good. And no, not even that you can conclude. You cannot conclude that 0 to 0 is 1. It's an indeterminate case. We could have come up with anything. And of course I shut my book. So this was a situation which is a power situation of 0 raised to 0. And we have 2 more to look at. Any questions so far? Any questions on this before we look at the next problem? Okay, so let's look at 63 caught my eye. Would you like to choose, or you want me to choose?
62 is fine.
Okay, and then you can choose the next one. So limit as x approaches 0 from the right, from 4x plus 1, raised to cotangent x. Yes, I cannot skip that. I have to see what this situation is. And obviously the base approaches when x approaches 0, this approaches 1. And cotangent, remember cotangent, a side note, is cosine over sine. So at 0, sine is 0, so this is undefined. So the graph of cotangent is this. Between pi 0 and pi, which is positive. Sorry. First quadrant positive, second quadrant negative. What am I thinking? So the right-hand side here is infinity. So as x approaches 0 from the right, this approaches infinity, and here is our next indeterminate case. So 1 raised to infinity. The mechanism is the same. The procedures, the steps are identical. So in the first step, I have to write y equals 4x plus 1 raised to cotangent x. And step number 2, I apply natural log to both sides. In the next step, I have to apply the limit to both sides as x approaches 0 from the right. And now I continue, and of course I have to check. Cotangent, as x approaches 0 from the right, this approaches infinity. And this approaches, when x approaches 0, this approaches 1, natural log, this is 0. So we changed the 1 to infinity into 0 times infinity, which we really like because this one requires an algebraic manipulation to change it into L'Hopital's rule cases. So then limit, x approaches 0 from the right. I'm going to change this into 1 over tangent. So 1 over tangent is cotangent. Now we are in business because this is 0 over 0. Tangent 0 is 0. Natural log 0 is 0. Natural log 1 is 0. So then we apply L'Hopital's rule. So notice that the power, again, the power situation went through the product situation to the L'Hopital's rule cases. Okay, so let's see. Let's differentiate the top. 1 over 4x plus 1 multiplied by 4, and the denominator is secant squared x. Let's see what we get. So luckily the denominator is nice because it's 1 over cosine squared, and 0 is 1, so this is 1, very nice. The numerator, when x approaches 0, this is 0, 4 over 1 is 4. But this is not done, right? I have to, in the last step, I shouldn't say last step, 2 more steps. I have to copy the beginning and the end. So I'm copying. Any questions? Any questions? Okay, I'm copying natural log. I'm copying the limit first. Limit as x approaches 0 from the right of natural log y is 4. At this point, under conditions of continuity, and this is a continuous function, to the right-hand side of 0, I'm allowed to swap the operators. I put natural log outside and limit, and I copy the function now. 4x plus 1 raised to cotangent x is 4. By the property that we just mentioned, that any log equation can be changed into an exponential and vice versa, we are able to identify and solve the problem, identify the limit. Can anyone tell us what will the limit be? The limit would be
e raised to 4.
excellent. And no, don't tell me that you would have known that from the indeterminate case 1 to infinity, that you would have come up with e to the 4th. I would not believe it. I'm kidding, of course. Any questions? Any questions? Okay, we have one more to illustrate with an example. They're all the same, as you've noticed. All the powers are treated in the same way, the products in the same way. L'Hopital's rule is L'Hopital's rule. Okay, so let's take a look at 62. Would you like to choose, or you want me to look at, we would like to look at 62?
Everyone is fine.
62 then. So we have limit as x approaches infinity from e to the x plus x, and everything raised to 1 over x. Yes, we have to check and see what the situation is here. Well, obviously all this is going to infinity, and obviously this goes to 0. So we finally get into the last indeterminate case, infinity raised to 0. Yes, it's a power indeterminate case, so I know what I need to do. The same procedure, step by step. Y equals e to the x plus x raised to 1 over x. We apply natural log. And then we apply limit to both sides as x approaches infinity. So limit as x approaches infinity from natural log y equals limit as x approaches infinity from this ratio. Okay, I try again, and I really like it. Here I don't really need to do anything. In this particular case, it happened that from here it jumped here without any intermediate step, which is fine by me. So we apply L'Hopital's rule. Limit as x approaches infinity. The denominator is 1. The numerator is 1 over e to the x plus x times e to the x plus 1. And now we are looking at this fraction, rational expression, so again, infinity over infinity. I apply L'Hopital's rule again, and I get e to the x, and the denominator is e to the x plus 1. Who cares? This is infinity over infinity, but when I differentiate again, I get e to the x over e to the x, which is definitely 1. In order to finalize this, I have to go and copy the beginning of the limit and the end of the limit. So I copy limit as x approaches infinity from natural log y equals 1. At this point, I'm allowed to swap the operators. Natural log of the limit as x approaches infinity. Now instead of y, I copy the function. E to the x plus x raised to 1 over x is 1. In the same way, we know what this equals to. So therefore, limit as x approaches infinity from e to the x plus x raised to 1 over x equals?
Is it B?
Very good. And again, no one can predict this. Infinity raised to 0 to end up being e. That's why these are called indeterminate cases. No one can predict anything. Anything can happen.
So the whole trick with almost all of these is just to get them to manipulate the function to one of the ratios. Okay.
Because that's what we know. The rest are, yes, all the powers are treated in the same way, with a natural log and a limit and swapping of the operators. And the idea is somehow to get this involved if possible. Sometimes in some problems we went through the product and then here, because this is a simple algebraic manipulation if it's possible.
Do we have to know now, like, what to do if it is not possible? If it's not possible,
No,